Hello, class, and hopefully future colleagues. My name is Douglas Engel, and as required for the 5550 final project, I'm creating this video to go through my final project. Today is December 9th. No, today is December 8th. Actually, it's due December 9th. So, but you'll probably be reading this afterwards. So, to start out, I wanted to start with the beginning, part A, which is pretty simple, really. It's simply to find a data set of images or audio files that could be used in some type of a machine learning application. So I looked around on Kaggle. I found this called the Database of Faces. It is originally created at Cambridge University Engineering Department. I believe AT&T was involved in it somewhere, but it's essentially 40 distinct subjects, and with let's see how many pictures are there of each person, taken at varying times, varying facial expressions, 40 directories, and yeah, there were 10 images of each subject. So here's an example of one of the subjects and the different views taken of it. This is all done in Unix, so the file system was not anything that was readily readable in Windows, but I did find a Irfan view, which is freeware online. And I was able to look at the images and get these screenshots here. So pretty basic part of the assignment. So moving on to the second part was to obtain the CIFAR10 data set. There were no submission requirements in here, but I went ahead and snapped a screenshot of my Jupyter Notebook environment showing the data happily sitting in the proper directory up on the Google Cloud platform. Part 3, a little bit more involved, was to build, train, and test a convolutional neural network on the CIFAR10 data set, and what was my approximation of the diagram indicating the dimensions of the input data, the convolution layers, and things like that. So not sure if it's 100% accurate, but to the best of my ability, I created that. And the punchline here for this one is that we got a 68% accuracy achieved. What I did is I took the output from the Jupyter Notebook file and copy pasted it into a spreadsheet, plotted it by step number or whatever. So I'm actually running my, well, I can show you how to do that real quick. So here is the data. So what I do is I just copy it in there and I just apply a filter across all the numeric values. So I get those. Then I paste them into this tab and I plot them as such. So no big deal. But fortunately, I did the same thing on homework number 4, just for grins, and it turned out to be pretty handy in part 4 when you had to do an actual comparison. So anyway, I running Google Cloud Platform from a virtual machine that I access via a remote desktop. It gives me another environment, Google account. I had to create another Google account in order to not have any dots or underscores in it or whatever. So, but this is this says part 5 code here. It's pretty much identical to the part 3 code and then I just went around and tweaked on some of the parameters to try and improve the performance a little bit. So yeah, that's how that works. So time we can go in here. All right. Yeah, so we started at 8:50. Okay, sorry about that. So this is the code. You know, obviously Dr. Nguyen gave us a great deal of it. But you know, going through here, for all the steps to unpack the data is zipped up, so it has to be named, and labels have to be applied to the different categories, and then you know, we wanted to display some of the example images in the data. And again, this is more code that was given to us. Set up image data, make it ready to be fed into the first convolution layer. A lot of stuff that I'm doing on my own. And then here is when we were required to start adding stuff in there. First is to initialize the filter weights. The default filter standard deviation was 0.1, but this is the part 5 example. This is the one thing I changed, where I actually got a little bit of a improvement in the accuracy. I decreased the filter weight standard deviation to 0.05 from 0.1. Everything else in this is the same. I tried a lot of different parameter changes, which I'll talk about later. But again, here's 3 of the things. We had to initialize the bias, and then define the first convolution layer. Obviously, import TensorFlow, you get all of those deprecation warnings, and you know, you have to define the relay layer, the pooling layer, fully connected layer, and then again, this was provided for us. The placeholders for inputs X and Y true. We were informed that this data did not need to be reshaped. It was clean enough the way it is, so that saved us some time there. The first convolution layer has filter shape 5, 5, 3, and 32. The pooling layer feeds in here and create the second convolution layer. It's a 5 by 5 filter, 32 input channels, 54 output channels. And they are specified here. The second pooling label into the spatial size here. We need to reshape and flatten data with this. First fully connected layer, another for the dropout layer. The hold probability is specified later in the code, but that's another one of the things I tried tweaking to get better performance with no luck. The last fully connected layer in the loss function, and then the optimizer set a learning rate of 0.001. I tried tweaking that parameter too. And that really messed things up. I tried setting the learning rate to 0.01, and it just performed horribly. I never got above 10% accuracy. And then the trainer and the variables initializer are standard from the classroom model. Okay, and then here's the, we define the number of steps as per the assignment, 5,000 steps. In the TensorFlow section, it goes through these nested for and if loops to give us our accuracy every 100 steps, starting at 0 all the way up to 4,900. So it gives us 50 data points. Again, this is the one where I got almost 70% accuracy. So that was something to report. I had been told not to not to expect a great deal of improvements in accuracy on classroom models. So that's where I left it. But you know, it worked and within expectations, I guess. And so moving on, part 5 was to compare the convolutional neural network performance between the 50 data points for the MNIST and the CIFAR10 data sets. And again, since I had collected the data from homework 4, it was pretty easy for me to go in here and plot them side by side. This is the results I got from homework 4, and the results I got from this CIFAR data set. And as you can tell, it's quite a big difference. It's about a 30 percentage point difference in accuracy here. It's pretty apparent. The best way I could explain it is that the MNIST data is much simpler structure, and there's fewer features that have to be learned. First of all, it's only 2 colors. I guess it's grayscale, and again, even though there are 10 classifications in each, the CIFAR10 data set contains multiple colors and more complex images and features, you know, airplanes and animals, different types of automobiles. So in other words, it would take more input data and or more computing horsepower to increase the accuracy of this CNN. And since the models are essentially the same, there are classroom 2-layer CNN models. The only thing I could really think that would be causing the difference is the source data. It's not that the source data is bad in the CIFAR, it's just more complex. And, it only makes sense that it would be more difficult to get an accurate result with it. So moving on to part 5. Part 5 was to try and improve the convolutional neural network performance. Again, as I mentioned earlier, there were quite a few different parameters. I only documented 2 of them here, just to kind of give you an idea. First tried increasing the bias value from 0.1 to 0.2, and the code below shows the original value. But use your imagination, imagine 8.2 in there, and I ran it, and the maximum accuracy actually decreased slightly to about 67. So I lost about one percentage point there. So that's not good. So, but the one I did have a little bit of luck with was decrease the filter standard deviation. The default was 0.1. I decreased it to 0.05, and I got almost 70% accuracy on this one. And it was the best. I don't know if it was the best or the only improvement I got in the compared to the classroom model. So that's the one I'm turning in as part of my part 5 Jupyter Notebook file. So that's what'll be in there. There's the chart. Now I went a little bit nuts and started Googling around and did find a pretty cool set of Python code GitHub done by some guy. I've cited him, referenced him, and all this stuff too. And I'm going to put the link to this in the not the comments, but the video thing in YouTube. I'm going to put a link in there if you guys want to take a look at it. It's pretty cool, and I thought I'd take some time to show it to you. It's pretty nice, nicely done. That I just simply, all I had to do was download it and change this line of code. I just put, there's their variable. I just put my directory name in there and ran it. It just ran. It's very well documented. you're using all the markup, fancy markup stuff too. There's information about the source data set, instructions for downloading it. But I wanted to use our data set because I wanted to be absolutely sure I was using the same data set. So I'm not saying I understand everything in this, but it's got some pretty cool features in it that I'll show you. There's all the labels here. Yeah, some of these modeling notes are really good. I don't have this in my document, but it shows the actual convolution steps, or the way it transposes the data in here, and that's very instructive. So if you really want to learn this stuff, I would highly recommend downloading this or whatever. So it also has some exploratory stuff in here. It does, like for example, I did put this in my document. Basically a sample of the database. It gives you batch number 3, number of samples out of 10,000. There's 994 airplanes, 1042 automobiles, and it's just interesting stuff to know about the data that you're dealing with. And it's all coded in here how they did it. And the preprocess function. We give you some of the theory in here as well too. I think would be helpful because I think I took a peek at homework 5, and I think there's a lot of theoretical stuff in there, which a little bit of advice. This might be. I'm just thinking of this right now, but this may be useful when doing the final homework assignment. I've talked to Dr. Wynn about this, and he's okay with us reusing code from other people as long as we reference it and properly cite it and represent it as our own and all that too. So this is all on the up and up. So yeah, some good theoretical stuff in here. The diagrams, how the different batches are split up between training batches and validation sets, and all this stuff. So that's all very good. And a lot of good reference material here. This is the kicker here. I'm counting 1, 2, 3, 4, 5, 6, 7, 8 convolution layers. 1, 2, 3, 4. I don't know if you count the output layer, but it's at least 4 fully connected layers in this model. So it is a monstrosity, but it all runs clean. And here's sort of a narrative description of the way the model's put together. And again, a little bit more about this conceptual convolving operation. And these are all the layers here, the hyperparameters. They do it in epochs and batch sizes. And then you'll probably recognize these peak probability, learning rate. They use the same learning rate that we did in the classical model. I think our keep probability was 0.5, but for this, whatever they used, 0.7. All the logic stuff. And okay, here we go, the training part. And this is what takes a long time to run. It probably took about a half an hour for this thing to run completely. Of course, it's up on the Google Cloud platform, so I guess it would probably be the same for all of us. But looky here in the training part, we got up to 76%, which is a pretty significant increase in accuracy. Of course, when you consider all those layers and all the computing horsepower and memory it must take to do that, it's maybe that's not that much, but it was the best it was the best I was able to get, at least compared to the classroom examples. So, but then there's some more cool features in here. That, okay. First of all, the full-on testing accuracy comes out to about 74%. So the training accuracy is a little better than that. And then there's some other cool stuff. Print random samples. So this part here is separate from this part here, but there's a thing where it just takes random samples and prints them out. You can see it's getting them right. That's an airplane, that's the horse, that's an automobile. I guess that's the horse. Yeah. It's even a stealth fighter that picked that up. So it's pretty beautiful. Then there's this the softmax predictions. I guess it randomly selects different classifications and determines, what they may be confused on. It looks like in this run, or I ran this a couple of times. In this run, it looks like, deer gets it right on deer most of the time, but it occasionally mistakes a deer for a cat or a bird, or something like that. Frogs, it does well on. I guess there's it looks like frogs or birds, but except maybe trucks and birds and deer sometimes get confused. But so anyway, like I said, this is I thought this was pretty cool. Glad to be able to share it with the class. Another interesting link in here is there are other classification results. Now this is results with the same data set, and that is here that there are not neural networks, but there are AI algorithms, I guess. They're not convolutional neural networks. They're just different types of neural networks that get, they say, up to 96%, 96% accuracy here. So, if you click on that, you get some details. You click on that, and I guess it takes you to Cornell University, and then the PDF here, and then there's some scholarly paper, about 10 pages long. It's mainly theoretical, but they don't just give you the code on how to do it. But I guess with enough effort, one could design this network as well too, and see if you could really get 98% accuracy out of this bad boy. So, what else? That's that. I did get another one from TensorFlow, but I never did. It wasn't as easy to modify and use our data with. Probably could just run it and download the data again here, but I never did run it. But this is actually from TensorFlow itself. It's warranted, and well, not warranted, but licensed. Whatever that means. So, all right. So I showed you the GitHub image classification, and it's got some of the highlights in there. Hyperparameters, validation accuracy, plotted this one too. Much of the this is a different run, so I got different random samples here. And then part 6 was a project report, which didn't make a lot of sense. I just assumed it was an opportunity to summarize everything that I did in the earlier part of the project. So, so there's a lot of back. I'm not going to sit here and read it to you, but there's a lot of background about convolutional neural networks, and they're useful for data and some of the applications, and a little bit about the Canadian Institute for Advanced Research data set. It's a collection of images that are commonly used to train machine learning computer vision algorithms, widely used. 60,000 32 by 32 color ranges, 10 different classes. part 3, again, was coded using our 2-layer classroom model. We got 68% accuracy. Part 4 is to analyze the differences between the MNIST, which is the Modified National Institute of Standard and Technology Database, handwritten digits. And again, I reiterated the difference of about 1/3 and attributed that to the more complex images. And then part 5 is what I summarized my attempts to optimize the model, increase its accuracy. To mention how the GitHub model gave us about a 6% improvement over the classroom models. And my conclusion, it's demonstrated that convolutional neural networks are extremely powerful. Of course, they have varying efficacy depending on the source data set. Another thing I've learned is that there's no one-size-fits-all CNN. There are many ways it can be architected and multitude of parameters that can be tweaked, and a lot of moving parts, a lot of buttons to turn, I guess, a good way to put it. So, but the good news is that environments like Jupyter and Google Cloud Platform and TensorFlow, it's fairly easy to rapidly prototype different models. Just keep turning those knobs until you see an improvement. You know, looking at some of these scholarly papers, there is an academic mathematical way to maybe better model this, but from the reading I did, it's still, some of it's just still hit and miss. You know, try stuff, see what happens, or whatever. But so again, I'm just a beginner at this stuff. But to me, this stuff sometimes seems more like an art than a science. Maybe that will, maybe my perception will change about that over time as I work with this stuff more often. But that's the way it seems now. So in part 7, I'm going to put the YouTube link to this video when I upload it to YouTube. And I guess those of you that have been assigned to evaluate me will be getting that link as well too. I do have a reference section, AT&T database of faces, and then the CFAR. This is where that cool Jupyter notebook is that I have. So again, I will put that in the YouTube notes or whatever. I guess when you upload to YouTube, you can put a note in there or whatever. So I'll be sure and do that, and hopefully that'll help some of you folks out. And looks like I'm coming right up on 30 minutes. And, I guess the timing is about right. Once again, Doug Engel, look me up if you got any questions, and then it should be in the global address book at UNT. I'll be around another couple of semesters, through spring at least anyway. So feel free to look me up if you got any questions or comments or concerns. So thanks a lot, everybody.